how do we choose the ordering in the mass squared operator? In particular, remember that we have summations of the following form: 1/2 summation over n not equal to 0, alpha I minus n, alpha I n. Let me tell you that you have the same summation for the alpha tilde terms, and let me also tell you that I am omitting the other summation over the index I from 1 to d minus 2. This will be implicit in this lecture, so in this lecture I will not specify it, just for the sake of a lighter notation, but as I said, it is still implicit. We will now try to put this in normal ordered form, so this is important. We already heard this in quantum field theory, the normal ordering. It is a way to choose the ordering of operators. So in this case, we want to quantize the theory, we want to think of these alphas as operators. So this is how we remove the ambiguity. We restrict ourselves to normal ordering. Namely, what this means is that we consider the annihilation operators alpha I n with n greater than 0, they will be put on the right. And now let's start from this term, 1/2 summation over n not equal to 0, alpha I minus n, alpha I n. We can write it as 1/2 summation over n less than 0, alpha I minus n, alpha I n, plus 1/2 summation over n greater than 0, alpha I minus n, alpha I n. And in this case we are considering operators, so these two summations here will not be equal because of the commutation relations. Now we want to put this term on the right of this one, because in this case for n less than 0 this will be an annihilation operator and we want to put it on the right, whereas here in this summation this is already okay, it's already acceptable the way it is, because this is already the annihilation operator, whereas this is a creation operator. So let's do it. Remember that the commutator between alpha I minus n, alpha I n, this is equal to minus n, and it's due to the fact that here we have minus n, then we have era I, then we have delta n minus n 0. Now the generic component era I is equal to 1, but remember that we are summing over I, that's implicit. So we sum over basically the ones contained in the diagonal from I equal to 1 to I equal to d minus 2. So this era I is actually equal to d minus 2. Therefore here we get minus d minus 2 times n. Therefore we can write this as 1/2 summation over n less than 0. Here we get alpha I n, alpha I minus n. So we are simply rewriting this term by using the commutator, because remember that this commutator is alpha I minus n, alpha I n minus alpha I n, alpha I minus n. So if we put this term on the right, we can rewrite this, which appears here, like this. So here we simply have to subtract d minus 2 n, like this, and then we still get plus 1/2 summation over n greater than 0, alpha I minus n, alpha I n, and this is equal to this. Now this summation here will be exactly equal to this one. They are exactly equal because in this case here we have minus n and n, but n is less than 0. So we can sum this with this and we can get rid of the factor of 1/2. It will become 1 times the same summation over n greater than 0, alpha I minus n, alpha I n. Then we have plus d minus 2 over 2 summation over n greater than 0. So in this case, I am losing this minus sign because I'm changing minus n to n, and therefore the summation will be performed over n greater than 0, not n less than 0. So I have just simply changed the variable of summation, the index over which we are summing. I'm calling it minus n instead of n. So you will change from minus n to n here. So you have to sum this. And basically this summation means that you have to sum from n equal to 1 all the way up to infinity. Now this summation here seems problematic, troublesome, because it actually diverges. We have the summation from n equal to 1 to infinity of n. But there is a way to make it regular, to, let's say, to find a finite value by means of the so-called renormalization in physics. This is something that can be done. And this summation will tend to be the zeta function calculated at minus 1. Let me do it in this way. In particular, let me associate the following series from 1 to infinity, and then I multiply it by e to the minus epsilon n. When we let epsilon go to 0, this series will actually be the same as this one. So I'm not doing anything rigorous mathematically speaking, but try to follow me. And if I calculate this series here, I can use a mathematical trick. In particular, I can rewrite it as minus the derivative with respect to epsilon, and here I have the summation over 1 over n equal to 1 all the way up to infinity, e to the minus epsilon n. So when I take the derivative with respect to epsilon, I get back this thing here, and this can be written as minus the derivative with respect to epsilon. When I take the sum, I get 1 over 1 minus e to the minus epsilon minus 1. So I need to subtract 1 because this is equal to the series when I started the series at n equal to 0. But since the value of the exponential at 0 is equal to 1, we have to subtract 1. So that's why I'm simply subtracting 1. Now I want to expand this denominator in a series, because epsilon is small, so this is approximately equal to minus the derivative with respect to epsilon. We have 1 over 1 minus epsilon plus epsilon squared over 2 minus epsilon cubed over 3 factorial plus dot dot dot. And then this minus 1 here will not appear because when I take the derivative, it's simply equal to 0. And this is equal to minus d over d epsilon 1 over epsilon minus epsilon squared over 2 plus epsilon cubed over 3 factorial plus dot dot dot, like this. Let's rewrite it as minus d over d epsilon. Then I can factor out 1 over epsilon, and I get 1 over 1 minus, and here I get epsilon over 2 minus epsilon squared over 3 factorial plus dot dot dot. And now this term here can be represented as 1 over 1 minus x. This would be approximately equal to 1 plus x squared plus dot 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 when x is small, right? Therefore, we can write this as minus d over d epsilon, 1 over epsilon, and then, so let me rewrite it like this. Here I will put this curly bracket, 1 over epsilon, square bracket, then I have 1 plus x, which is epsilon over 2 minus epsilon squared over 3 factorial plus dot dot dot, plus epsilon over 2 minus epsilon squared over 3 factorial plus dot 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 squared plus dot dot dot. Then I close the brackets. And now let's consider the lower order terms. So we have 1 over epsilon, we have 1 plus, here we have epsilon over 2 minus epsilon squared over 3 factorial plus, then when we square this we have epsilon squared over 4, then we get plus 2 times this, so we get minus 2 epsilon over 2, so we get minus epsilon times epsilon squared over 3 factorial, so we get epsilon cubed over 3 factorial plus this term squared, epsilon to the 4th power over 36 plus dot dot dot, then higher order terms. And finally, we get minus d over d epsilon, 1 over epsilon plus 1 half minus epsilon over 3 factorial, which is 6, plus epsilon over 4 minus epsilon squared over 6 plus epsilon cubed over 36 plus dot dot dot. Now remember that epsilon goes to 0, so when we take the derivatives of these terms, or higher order terms, they will still contain epsilon, because the derivative of epsilon squared is 2 epsilon, so it is still linearly proportional to epsilon, and epsilon cubed, its derivative is 3 epsilon squared, and so on. So all these terms are negligible, because when we let epsilon go to 0, they will cancel. So we are only interested with this first part, because if we take the derivative, this part will not go to 0. Actually, we have one first term which will diverge. So let me put this minus sign here. So we have minus. Here we have minus. Here we have plus, and here we have minus. And all these terms here will, they will just cancel. Okay. So we get 1 over epsilon squared, and then we get plus 1 over 6 minus 1 over 4. And then this will be 1 over epsilon squared minus 1 over 12. And this is a finite part which we associate to the series, whereas this part diverges, but by an appropriate renormalization, we can get rid of the infinity thanks to renormalization. And I will not, of course, get into the details of renormalization, because it is a very huge topic, and I will just try to tackle it informally and intuitively. That's what I want to do here. But it can be renormalized, so the theory can be renormalized, and therefore this is the value that we can attribute to our series. So minus 1 over 12, which is something that seems strange, but it is something that we can do, because we can associate series of this kind for some integer s to the zero function. And this zero function is not divergent, but we can think of this as a one-to-one correspondence if you want. So the infinities in this kind of process will be lost. Therefore, we have to choose the following value for the series, minus 1 over 12. And if we go back up, here we replace minus 1 over 12. So here we get summation over n greater than 0, alpha I minus n, alpha I n. Then we get minus d minus 2 over 24. And this will be proportional to our mass squared operator. In particular, remember that the mass squared operator can be written in this form. So last time we wrote it as 4 over alpha prime. Then let's put again the summation over I to make it explicit. Here we put d minus 2 summation n greater than 0 alpha I minus n alpha I n. The same thing will hold for the tildes. So the alpha coefficients with the tildes. In this case, they are operators. And as I said, instead of considering this summation, we have to put minus d minus 2 over 24. Like this. So this is the definition that we will have to consider in our theory if we want to remove the ambiguity thanks to the normal ordering. And this same operator can also be written, as I said, with the tildes. Let me write it like this. So m squared can also be written as 4 over alpha prime, summation over I from 1 to d minus 2, summation over n greater than 0, alpha tilde I minus n alpha tilde I n minus d minus 2 over 24. Now we can define, for the sake of convenience, this operator here. So this is an operator because it is made up of operators. We can call it n, whereas we can call this one n tilde. They are some kind of number operators. So you should try to recall that from quantum field theory. They give us information about the number of excited states of the string, and it is not very difficult to understand why they are number operators. Because let's think about this one, for example. So this alpha in will destroy a state, so it will remove some energy, and in particular n quanta of the energy. Whereas this term here, when n is greater than 0, will create the n quanta. So it's as if we are doing the same operation back and forth. And therefore we get a constant, basically, when doing so. We get something proportional to the state. Then we are summing over I from 1 to d minus 2, and we are also summing over n. Basically, we are counting all the possible states of the string, because the generic state of the string can be constructed thanks to these operators here. And if some of these operators do not appear in the state, then this operator, for example, will annihilate that state because it will only directly act on the vacuum, and therefore we are not counting that. This is just the idea, but this is something that we have already seen also in quantum field theory. It's not too difficult to try to understand it intuitively. Anyway, this is where we'll stop for this lecture, but now we have come to a point where things start to get very interesting, because now we are in a position to understand which kind of particles arise from string theory. And we will soon get to the graviton and other very interesting particles.